Today we have question 2 from the University of Maryland math competition, part 2 from this year, where we're given that A is a set of numbers, and we sort of have this custom set addition definition, where A plus A is equal to X plus Y, where X and Y are distinct elements of A. And we're also given the definition or the notation of the size of a set. When I want to show that a set A exists such that A is a subset of 1 to 2025, and the size of A plus A over the size of A is equal to 5. Or in other words, the size of A plus A is equal to 5 times the size of A. And so to start, you might be curious, what is the maximum size that A plus A can actually achieve? That happens when all the pair sums, I guess you might call them, are different, right? None of them overlap. And so when that happens, then you just choose any two elements from A, sum them, and they'll give a different result. So in total, you'll have n choose 2, or I guess we first let the size of A be n, then we have the size of A plus A is less than or equal to n choose 2, right? You just choose any two elements, and none of the pair sums will overlap. And so n times n minus 1 over 2. And right, so we have an upper bound for the set for the A plus A now. And so you might, or like, the hard part of this problem is dealing with, when do two sums overlap? And so then A plus A, the size of A plus A is strictly less than this. And yeah, that's hard to deal with because, there doesn't seem like a nice way to determine when to, or to count which two sums will actually overlap given any set A. So you might sort of wishfully think that maybe there exists some special set A where somehow no two sums overlap, so we do achieve this upper bound size of n times n minus 1 over 2. And if that's the case, if no sum overlaps, then we immediately just have n times n minus 1 over 2 is equal to 5n, right, from this condition. Then if we can solve for n and then find, such a set A with size n, then we're immediately finished. All right, so here the n's cancel out, so n minus 1 over 2 is equal to 5, and so we have n is equal to 11. So if we can find a set A with size 11 and no two sums overlap, then we're finished. So you might start to, construct A sort of greedily, right? Start from the smallest numbers and see where you can get to. Right, you can start with 1, you can add 2, that's okay. You can add 3, that's all right. You cannot add 4, right? Because 1 plus 4 and 2 plus 3 will overlap at 5. But you can add 5 because you have none of the sums will overlap. But what about the next element? Can you add 6? You cannot add 6 because 1 and 6 and 2 and 5 will overlap. But you can sort of see, right, we're only at 4 elements so far, and I guess finding the 5th element seems like it will take a little long, but even if it didn't, right, we still have 6 more elements to go. And that would surely take, quite a long time to make sure no sums overlap. So I guess it'd be nice if not only if when we find this A, maybe there's some special A with some nice property or nice pattern that we can make use of to easily get a size of 11. And I guess the main issue sort of starts when we add these like 3 and 5s, where, they're not really nice numbers. But for 1 and 2, even though it's only two numbers, you might realize this is 2 to the 0, this is 2 to the 1. But what if we add 2 to the 2, right? We had 4 instead of 3. Then, see, we still have no two sums are the same. This is 3, this is 5, this is 6. And then we add 2 cubed, which is 8. Again, you can check no two sums overlap. And we can continue this all the way to 2 to the 10, which is 1024. Right, so we have all the powers of 2. I cannot draw. We have all the powers of 2 from 1 all the way to 2 to the 10. So we indeed have that the size of A is equal to 11, and no two sums overlap. And you can sort of see the second part, I guess, by viewing the sums in binary, right? So we have 2 to the 0 is 1 and 0, 0, 0, 0, 0, 0. It's 9 zeros we have to consider. 2 to the 1 is 0, 0, 0, 0, 0, 0, 0, 0, 1, 0. 2 squared is 0, 0, 1, 0, 0, 0, 0, 0, 0, 0. Anyways, all the way to 2 to the 10, which is 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. And you can see that, any two sums or any sum of two of these numbers will give two ones in different positions among, these 10 digits or these 10 places in binary. Right? Any two sums will give like a 1 here and a 1 here, or a 1 here and a 1 here, and everything else is 0. So, that means that any two sum will be distinct in binary and thus distinct in base 10 as well. So we do have that no two sums overlap, and this set of A satisfies the given conditions up here, and that means we're done.